Every complex number has n nth roots, and I've written the formula that will give them to us over here on the board. The nth roots of a complex number. The nth roots of z equal r cosine theta plus I sine theta, that is a complex number written in trigonometric form, are given by w sub k equal r to the 1 over n cosine theta plus 360 degrees times k divided by n. N is the root that we want, like second root, third root, fourth root, whatever it is, and k is equal to 0, 1, 2, all the way up to n minus 1. So if I'm looking for a fourth root right here, k is going to take on values 0, 1, 2, and 3. It goes up to 1 just before the number of the root I want. So this formula is derived for you in the book. What I want to do is go to the board now and work some problems in which we use this formula. So let's look at our first example. Let's find the two square roots of 2 plus 2i square root 3. Well, the first thing I need to do is write this number in trigonometric form. So I'll say z is equal to that, a is equal to 2, b is equal to 2 square root 3. That means that r is equal to square root of 2 squared, which is 4, plus 2 square root 3 squared, which is 4 times 3, or 12. So I get square root of 16, which is 4. Cosine theta is equal to 2 over 4, which is 1/2. Sine theta is equal to 2 square root 3 over 4, which is square root 3 over 2. So together, this implies that theta is equal to 60 degrees. So I have r, and I have theta. So my complex number z is equal to 4 cosine of 60 degrees plus I sine 60 degrees. Now I want the two square roots of z. So I want so my two square roots. Whoops. Let me erase that. Yeah, let's erase it. What I want to do is use this other notation. W sub k is equal to 4 to the 1/2 cosine of 60 degrees plus 360 degrees times k, all divided by 2, plus I sine 60 degrees plus 360 degrees times k, all divided by 2, where k is equal to 0 and then 1. So let's simplify this a little bit. This looks like 4 to the 1/2 power is the positive square root of 4, which is 2. And then I have cosine of 60 plus 360k divided by 2 is 30 degrees plus 180 degrees times k, plus I sine 30 degrees plus 180 degrees times k. So let me use brackets right here. Okay, so now when k is equal to 0, I get 2 cosine 30 degrees plus I sine 30 degrees, because I'm going to add 180 times 0 onto 30 degrees. And when when k is equal to 1, I get 2 cosine of 30 plus 180 times 1. 180 times 1 is 180, plus 30 is 210, plus I sine 210. Now if I want to, I can change these back into algebraic form. This is 2 times cosine 30 is square root 3 over 2 plus I times 1/2. And this is going to be 2 times, the reference angle is 30 degrees and 210 terminates in quadrant 3, so negative square root 3 over 2 and minus I times 1/2. So my two complex numbers, I'll multiply this out and I get this. Square root 3 plus I, that's one complex number, that's the square root of my original complex number, and the other will be what I get when I multiply these out, which will be negative square root 3 minus I. So there is my two square roots of the complex number. Where did it go? 2 plus 2i square root 3. So this complex number has two square roots, square root 3 plus I and negative square root 3 minus I. Now, if I want to, I can square this complex number, I'll get exactly this, or I can square this complex number, I'll get exactly this. Every complex number, which includes every real number, has two distinct square roots, and this formula right here will always give them to me. Next, I want to go look at a problem in which we find the 3 cube roots of a complex number. We want to find the 3 cube roots of negative 27. So our complex number z is equal to negative 27, and if I write that, and if I look at the graph of that real quickly, okay, it's going to be a vector that's 27 units long out to the point negative 27, 0. So that vector has a length of 27, and this angle right here is 180 degrees. So in standard form or algebraic form, it's negative 27 plus 0i. In trigonometric form, it's going to be 27 times cosine of 180 plus I sine of 180. So that's my complex number z in trigonometric form, and what I want to do is find the 3 cube roots of z. So here's my complex number z, and what I'm going to do is find the 3 cube roots of it. So using the formula then, I have w sub k, where k will take on different values and give me the 3 cube roots, will be 27 to the 1/3 times cosine of, I'm going to say theta sub k plus I sine theta sub k, where theta sub k is the angle 180 degrees plus 360 degrees times k, all divided by 3. And then k will take on these values 0, 1, and 2, up to the smallest integer less than 3. Now let me simplify this a little bit. 180 divided by 3 is 60 degrees, and then 360 degrees times k divided by 3 is 120 degrees times k. So I'll substitute different values of k into this. K equals 0, k equal 1, k equal 2, and for each value of k I put in, I'll get one of the angles that gives me one of the cube roots of z here. So let's do that now. So I have well, let's see. So theta sub 0 is equal to 60 degrees when I put 0 in for k. Theta sub 1 is equal to 60 degrees plus 120 times 1, so that's 120 plus 60, or 180 degrees. And theta sub 2 is equal to 2 times 120, which is 240, plus 60 degrees, which will be 300 degrees. So here are my 3 angles, theta sub 0, theta sub 1, and theta sub 2. So I can write my 3 complex numbers then as w sub 0 equals 27 to the 1/3, which is 3, cosine theta sub 0, which is 60 degrees, plus I sine 60 degrees. Then w sub 1 is 3 cosine of theta sub 1, 180 degrees, plus I sine 180 degrees. And then w sub 2, my 3rd cube root, is 3 cosine 300 degrees, plus I sine 300 degrees. Now what I want to do real quick is look at the graphs of my 3 cube roots. So let me draw on a coordinate system here. And what I'm going to do is graph each of these 3 cube roots so that you can see the relationships between the graphs of the 3 cube roots of this number. What happens is that the 3 cube roots divide the coordinate plane up into 3 equal little areas. So let's take a look at the graphs of these. So for theta sub 0, the length is 3 and the angle is 60 degrees. So that the graph of that complex number is going to be a vector 3 units long at 60 degrees up from the positive x-axis. The next one is also 3 units long, and it's at 180 degrees. So that looks like this, where that's 3 units long at 180 degrees, and the last one is at 300 degrees, and it's 3 units long. So that looks like this, 300 degrees, and it's 3 units long. So you can see my 3 cube roots are equally spaced around the coordinate plane like this. Now I can take each of these 3 cube roots and rewrite them in algebraic form. Let's do that in a different color here. This will be 3 times cosine 60 square root 3 over 2 plus I sine 60, whoops, take that back. Cosine 60 is 1/2 plus I sine 60 square root 3 over 2. So I end up with 3/2 plus 3I square root 3 over 2. That's that first complex number. The second one, I want to show you this, will be 3 cosine 180 is -1 plus I times sine 180 is 0. So that's just -3. But didn't we know that already, that one of the cube roots of -27 is -3? And usually in algebra, when we say let's find the cube root of -27, we say it's -3. Well, that's just one of the cube roots of 27. There's 2 other ones too that are complex numbers. One is this one, and the other one is what I get when I do this. So cosine of 300 degrees, that's in quadrant number 3. The reference angle is 60 degrees, and so the cosine is square root 3, whoops, I'll do that again, is 1/2 plus I times the sine of 300, negative square root 3 over 2. So that's 3/2 minus I square root 3 over 2. Or, I'm sorry, 3, let's do this right, minus 3I square root 3 all over 2. So here is my other root of this complex number, and so I have this root, and this root right here, -3. Now I don't want to leave this problem yet. I want to do a little bit more on it. But I did want you to see, first of all, the 3 cube roots in trigonometric form. When I graph them, they divide the coordinate plane up equally. Now that will happen with 4th roots, 5th roots, 6th roots, any number of roots. They will always be equally spaced around the coordinate plane. Second then, each of these complex numbers, when I convert it into algebraic form, you see we recognize the one that we have from algebra. Now, just to justify what we've done so far, in algebra, if we were to say find the cube roots of -27, it would be the same as solving this equation. X cubed equals -27. So if we wanted to solve the equation x cubed equal -27, we'd put it in standard form. X cubed plus 27 equals 0. Then we would factor this as the sum of 2 cubes. X plus 3 times x squared minus 3x plus 9 equals 0. I set this first factor equal to 0, and I would have x equal -3 as one of the solutions. And there is that real cube root of -27. When I set my other factor equal to 0, x squared minus 3x plus 9 equals 0, it doesn't factor, so I have to use the quadratic formula. -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. And I end up with 3 plus or minus, this is 9, subtract 36, so that's -27, which is 3I square root 3, and that's all divided by 2. And there are my other 2 cube roots exactly like I got them over here. Those are the other 2 cube roots I've got. I've just written them in this form right here. So this was a problem that I could have done algebraically in the past by solving the equation x cubed equal -27 to find the 3 cube roots of 27. In trigonometric form, I have another method of finding those exact same 3 roots using this formula that I have for finding the nth roots of any complex number. Okay, let's do one last problem that involves 4th roots. I want the 4 fourth roots of z equals 16 cosine 120 plus I sine 120. So, as far as my formula is concerned, let's write r sub k is 16 to the 1/4, that's the number 2. That will be the modulus or absolute value of each of my roots. Theta sub k will be 120 degrees plus 360 degrees times k, all divided by 4 in this case because I'm looking for 4th roots. Now let's do that division. 120 divided by 4 is 30 degrees, plus 360 divided by 4 is 90 degrees, times k, where k is equal to 0, 1, 2, and 3. So here's the formula for the modulus or absolute value of each of my roots, and then here is the angle or argument of each of my 3 roots. So let me write my 3 roots by substituting in 0, 1, 2, and 3 for k in this formula. So I'm going to have my first root, w sub 0, will be 2 cosine of 30 degrees plus I sine 30 degrees. Now I want to, at the same time here, make a little graph of these 4 fourth roots. So let's do that with this first one that I have, 2 cosine 30 plus I sine 30. So here's 30 degrees, and I want this to be 2 units long. So that vector right there, that is the graph of this complex number. Now, since these are 4 fourth roots, I know they're going to divide this coordinate plane up equally, so I can actually draw the graphs in right now. I'm going to have to go another 90 degrees. That will give me the graph of this complex number is 2 units long, and it will be at 90 plus 30, which is 120 degrees. 90 degrees past that, a vector 2 units long, is one of the other roots, and 90 degrees past that, another vector 2 units long, which is one of the other roots. Now let's see if these 4 complex numbers that we've written here, their graphs, match what we get when we apply the formula. And of course they do. W sub 1 is 2. Cosine of, okay, I have 30 degrees plus 1 times 90. That's 90 plus 30, or 120 degrees, plus I sine 120 degrees. And that's this vector right here. W2 is 2. Cosine of 2 times 90 is 180 plus 30, 210 degrees, plus I sine 210 degrees. And that, of course, is this vector right here. That's 30 degrees past 180. And then my last root, 2 cosine of 3 times 90 is 270, plus 30 degrees is 300 degrees, plus I sine 300 degrees. And of course that's this, has as its graph this vector right here, which is at 300 degrees, okay, and it's 2 units long. Now I could take each of these 4 roots right here and evaluate cosine and sine of the angles and write them in algebraic form, but I won't do that in this case. It's really a pretty simple process. What I want you to see is, here are my 4 fourth roots, and when I graph each of them, they divide the coordinate plane up into 4, they're equally spaced around the coordinate plane, which means that I could have just found this first one right here, and then drawn in all the rest of them and actually written the formulas right from the graph if I wanted to. Now you might want to practice that on some of the problems that you do on the assignment. So the point of this section is this. Every complex number, which includes every real number, has n nth roots. That's 2 square roots, 3 cube roots, 4 fourth roots, so on and so forth.